A very good morning, students. In today's class of fluid mechanics and machinery, we will see about the velocity triangles of turbines. Hydraulic turbine, classification of hydraulic turbine, hydroelectric power plant, velocity triangles of Francis turbine, Pelton wheel turbine, velocity triangles, and assessment. So before going into the slides, first we'll study about what is the difference between a pump and a turbine. A pump converts mechanical energy to hydraulic energy and by using the external power, but a turbine utilizes the hydraulic power of the water to mechanical, and in turn it is connected to a gear mechanism. Then it converts the hydraulic energy to mechanical energy to the electrical power generation. So we have different types of power plants. So one is thermal power plants, second is hydroelectric power plants which use water as the hydraulic energy of the water, and steam turbines we have. In power plants they use steam turbines, and we have wind turbines also which utilize the kinetic energy of wind. So now we move on to hydraulic turbines. Hydraulic turbines are nothing but the machines or device which converts hydraulic energy into mechanical energy is called as hydraulic turbine. So it is mainly classified as Pelton wheel turbine, Francis turbine, and Kaplan turbine. Classification of hydraulic turbines based on the energy at inlet and according to the direction of flow through a runner. So according to energy, it is impulse turbine and reaction turbine. In impulse turbine, kinetic energy is maximum than pressure energy. Example, Pelton wheel turbine. Pressure energy is maximum than kinetic energy. Then the reaction turbines. Example is Francis turbine and Kaplan turbine. So according to the direction of flow through runner, so it can be a tangential flow where the flow along with the tangent of runner in case of Pelton wheel turbine. Radial flow when flow enters the radius through runner. In axial flow, the water flows along the direction of rotation of runner. In mixed flow, water inlet radial direction and exit in axial direction. So classification of hydraulic turbine according to the flow through runner. So tangential flow, radial flow, and axial flow and mixed flow. Classification of hydraulic turbine according to the head availability at inlet according to the specific speed of turbine. So low head is less than 60 meters. So Kaplan turbine is used. Medium height, if the head of the water in the reservoir is between 60 to 250 meters, then we can use Francis turbine. So high head in which is an example of a dam. So any Meto dam power plant. So it is all high head dams or high head meters. So 250 meters, greater than 250 meters of head. So we use Pelton wheel turbine. So according to specific speed of turbine, so low specific speed is less than 60. So they use Pelton wheel turbine. Medium specific speed 60 to 300 meters per second. Then they use Francis turbine. So if the high specific speed 300, greater than 300, then they use Kaplan. So this is a typical diagram of an hydroelectric power plant. So from the diagram we can see, so there is a reservoir, so which has a water, which has a head raise, and head raise is nothing but the highest level of the water in the dam, and they will have a dam. So from the dam the water is sent to the turbine through a penstock or through some channel or pipe. We call that as a penstock. Surge tank, valve house. So according to the requirement, then they will open and close the valve. And the turbine house, so where the penstock is the inlet, we call that as a tail race. So the hydraulic energy of the water, which will turn the turbine. In turn, the turbine will be connected to a gear mechanism, and the gear will, the one rotation of the turbine, so will be converted to 1,000 revolutions, and in turn it will generate the kinetic energy or the pressure energy of the water will be converted to electrical energy, and it will be sent to the grid directly. So this is the hydroelectric power plant. So there is a dam, a well constructed across the flow of river, penstock, a pipe which convey the water from dam to turbine house, assembly of runner, shaft to convert hydro energy into mechanical energy. A surge tank is there, surge tank fitted on penstock before valve to avoid water hammering, valve house to control the rate of flow of water through penstock. Next we come to velocity triangle. So we could have seen the velocity triangle diagram for a pump. So similarly, so we have the velocity triangle for a turbine. So turbo machinery, a velocity triangle or velocity diagram is a triangle representing the various components of velocities of the working fluid in a turbo machine. It is actually the where the inlet angle is there, so it will be opposite to the pumps in turbines. So velocity triangles may be drawn for both inlet and outlet section of the turbo machine. A general velocity triangle consists of the following vectors: V, absolute velocity of the fluid; U, blade linear velocity; VR, relative velocity of the fluid after contact with rotor; VW is the tangential component of velocity, absolute velocity called Vril velocity; VF is the flow velocity at the inlet. So it can be an axial machine or radial in case of radial machines. The following are the angles encountered during the analysis. So alpha is the angle made by V with the plane of machine, usually the nozzle angle or the guide blade angle. Beta is the angle of the rotor blade or absolute angle. So this is the velocity involved. So V1, VW1, these are the inlet velocities. So for example, denotes the high pressure side, inlet in case of turbines, outlet in case of pumps. So this one, V1, the subscript denotes the high pressure side, inlet in case of turbines. High pressure will be there due to hydraulic energy. In pumps, So from low pressure to, we transfer the water to high head through high pressure through a pipe or using a pipe. So velocity triangles of Francis turbine. Turbine run blade inlet and outlet under different operating conditions: maximum wicket gate opening conditions, peak efficiency conditions, and minimum wicket gate opening conditions. So outlet will be U1, VW1, VF. Here inlet will be V2, U2, VW2. Pelton wheel turbine velocity triangles. So it is actually the opposite of the pump. So pump, the outlet we will have the V2, U2, VR2, VW. So here the inlet will be in high pressure. So U1, UR1. So V1 is equal to VW1. For Pelton wheel turbine, the velocity triangle is high speed turbine. So here also the same. The angle at the inlet is, so this will be rotating in the clockwise direction. So in pump it will be anti-clockwise direction in the, according to the axis, flow of axis, then we'll say the angle. So here it is clockwise direction. So inlet is U2, VR2, VF2, V2, and the angle is phi. Francis turbine. So here also the turbine is, the inlet is VR2, V2, VF2, U2, VW2. At the outlet the pressure will be less. So VU1, VW1, V1 is equal to VF1. So here also the angular velocity omega is there. Radius R1, R2. R1 is the distance between the distance from the center to outlet of the turbine, and inner radius is R2. Thank you.